So I'm Alexei, and this is Zia. I'm very excited to be here together with Zia because together we represent the two organizations that brought to the world the first neutral atom quantum computer that's publicly accessible, the machine Aquila that has been built by QuEra and then launched in November 2022 on the Amazon Braket service. And it has been operating ever since. It's available to everybody today. And our presentation today is focused on that story, the life cycle of the machine, of the service, and the customer successes that it brought to the world. So first, I will tell you a little bit about the full gamut of services and products that QuEra offers in terms of neutral atom quantum computing, and then I will focus on the evolution of Aquila and the AHS service. And AHS stands for Analog Hamiltonian Simulator. That is the mode in which the machine is programmed. And then Zia will talk about how to use that machine through the service on Braket and highlight a few of the customer and application successes. So you see the picture of the two machines that QuEra has built. The one on the left is the Aquila machine, and that is in the headquarters in Boston. You see the NATO delegation posing in front of it. It is the machine that you can access via the cloud. The one on the right is actually our first gate-based quantum computer that we are currently installing at the AIST in Japan. It will be our first on-prem quantum computer, and we will be integrating it with the HPC environment over there. So between these two machines, they represent both the analog mode of quantum computing, the digital mode of quantum computing, the cloud delivery to the customer, and the on-prem HPC delivery to the customer. As a next step, we will be trying to offer the analog machine as an on-prem solution and also offering cloud access to the machine at AIST and other gate-based machines that we have. And hopefully that really addresses many of the needs that early adopters in the market today have for using quantum computers and neutral atom quantum computers in particular. For those who are curious, are these just black boxes or can I do something with them? So these two papers actually represent the state of the art of the things you can do with these quantum computers. The one on the left is kind of the first demonstration of string breaking. It is a phenomenon in the dynamics of lattice gauge theories and high energy physics. And that was done on Aquila. The one on the right is actually the world's first demonstration of logical magic state distillation. And that is a critical ingredient of universal fault-tolerant gate-based quantum computing. So you can see that these machines are really pushing the state of the art in physics, in quantum computing, and later on, Zia will tell you more about more industry-oriented use cases. Taking a step back, I told you about the analog machine. I told you about the gate-based machine that can actually be programmed to do some error correction as a testbed for error correction. And of course, we're moving towards the fault-tolerant era where users will be able to program at the level of logical qubits with much, much lower error rates. In fact, we're already starting construction of multiple machines of this generation at QuEra headquarters. They're not yet available to users, but we hope to offer them pretty soon. And in the context of the evolution of the technology in our product through these three generations of machines, I want to tell you a bit about how we use that evolution as an opportunity to develop software tooling, specific products, and customer partnerships through these three generations. So first, with the software tooling, our analog quantum computer Aquila had to develop the API model. We launched the open source SDK and simulator blockade, and of course we integrated with Amazon Braket as our cloud provider. For the gate-based machine that is now setting up at AIST, we're building compilers, defining different levels of abstraction at which users can interact with the machine, and of course, we're starting this whole HPC integration story. With the logical qubits of the next generation machine, this HPC integration story will become even more important as a way to do scalable decoding of quantum errors. And once those quantum errors at the logical qubit level become low enough, we're really thinking about application verticals for real business use cases. The specific product, I already talked about Aquila. The service or the mode of interaction with it is analog Hamiltonian simulation and cloud service. Gemini It's our first on-prem installation. It is also a platform where we are trying to start hardware, software, application co-design with our customers to really make the best use of the kind of this NISQ era quantum resources of that machine. And once our logical qubit machines can be made at scale, we really hope that they will become kind of OEM devices that customers can buy and integrate into their own systems and workflows. Throughout this whole story, we had the opportunity to develop many key relationships and partnerships, starting, of course, with Harvard and MIT, where we have our origins, AWS, which was our first kind of go-to-market, national labs, DOE, DOD, QuEra Quantum Alliance of private industry partners. In the context of this gate-based machine at IIST, it's our first on-prem installation, and we're trying to build a relationship with the Japan ecosystem, as well as in the UK with the NQCC. Google Quantum AI was our Series B investor lead, and we're working with them as well. And going forward, looking forward to the logical qubit era of fault tolerance, we're already starting on kind of the path to utility through the DARPA QBI program and the collaboration with NVIDIA, where we hope to figure out how to do scalable decoding of quantum errors. Now, returning to Aquila, I do want to focus on the story of that machine from when it was first launched in November 2022 and see how that evolved, because I think there is a set of lessons that we will be applying to many of our deployments and future generation machines. So our first launch on AWS was cautious at 10 hours a week because many things weren't figured out yet. And as we kind of continued to operate it for customers, we realized, first of all, there were many more people willing to use the machine than we had machine time available for them. And the first thing we did was expand to 50 hours a week, almost 5 times the machine availability. We also developed software development kits, simulators, and soon after that, we expanded the service further to 130 hours a week. Soon after that, AWS launched the Bracket Direct service, which allowed machine reservations and experimental features to become available to users. And then after that, we used this new model of Bracket to actually offer new features on Aquila that drove further use cases and customer traffic to the machine. New features in this case included local control of the Hamiltonian that enabled things like quantum machine learning and some of these lattice gauge theory simulations that I showed in the earlier slide. So these were kind of public feature releases with Bracket. And here I just want to highlight a few of the customer impacts, which are very diverse. Everything from hackathon to premium access for national labs, papers published by industry users that are doing proof of concept projects on the machine. DARPA got involved and funded machine time for application developers from a number of different research groups. Papers on quantum simulation and machine learning, and many, many more. Now, while all of these feature releases were happening and all of these customers were getting access to the machine, we were working hard to improve the operational model and the machine itself under the hood, including reducing technical debt that we started with and adding a number of software features that really allowed us to reach an operational maturity that we can be proud of. So at the end of all of that story, we kind of reached 99% uptime of the machine that was essential to giving the users confidence in the consistency of the service. And that is one of the key things that, together with AWS, we believe that has continued to bring customers to the machine. To highlight the actual impact on the users as a statistical measure, this is actually traffic on Aquila through AWS. On the top, you see the cumulative tasks ran on Aquila through Bracket, and on the bottom, you see the cumulative shots ran over the 2.5 years that it has been in the service. So the blue is the year 2022, orange is year 2023, and black is year 2024. And you can see that the slope of these curves is going up year to year. That basically means that the usage is going up. You can also see that there are some discontinuities where there's major upticks in traffic, and those are actually correlated with two things. One is this expansion of service to match the demand. And the other one was the launch of new features in Aquila that really offered a range of new use cases and new opportunities for customers to try new things. All in all, by this point, after 2.5 years of operation, there are 23 papers out there citing results from Aquila, and importantly, 15 of those do not involve any QuEra scientists, which really proves the point that you can't offer this as, this quantum computing as a web service and let users achieve impactful results without kind of experimentalists in the lab doing the work for you. And so this is a model we would love to kind of carry forward with our on-prem installations and future cloud service machines. With Aquila, what have all these users been doing? 23 papers. There's actually kind of these problems divided into 4 quadrants. There's classical and quantum problems, and there are equilibrium and non-equilibrium dynamics that you can study with the Hamiltonian evolution on Aquila. And so the types of problems that have seen kind of interesting results were optimization problems, machine learning problems, quantum simulation in the area of quantum phase transitions, and of course, this lattice gauge theory work. So with that, I will actually hand it off to Zia, who will tell you more about how do you use the machine on Bracket and what are some of the industry use cases.
Awesome, thanks, Alexei. Appreciate it. So, so far we saw how the relationship between AWS and QuEra has been going. One thing that I'm here to tell you about is how the QuEra device fits in and what we're doing at Amazon with some customers to actually get their hands on this device. But first I wanted to start with, what is the Amazon Bracket quantum stack? How do we kind of fit in, and where do devices fit into that? So at the very foundational layer are infrastructure and access modes for accessing quantum computers, such as the QuEra device. You'll see we have QPUs, simulators, and then GPUs and CPUs. One of the trends that we've heard at the conference is around how quantum and hybrid classical computing are coming together in these hybrid workflows. On top of the infrastructure layer, we provide platform tools. So Blockade, which is the QuEra SDK, but we have managed Jupyter notebooks through SageMaker. We have hybrid jobs, which is our quantum classical runtime. Then we also have local simulators, really building into that, hey, test something, run it locally, and then go and run it on a device. And then at the top of the stack, we have services for corporates and enterprises to get them to discover use cases. How are people actually using quantum? We also have something with experimental capabilities, which I'll touch upon in a sec, to make sure that researchers, scientists are getting access to the latest capabilities of a device on Amazon Bracket. And so this holistic picture is what we've built out for accessing devices and software through Amazon Bracket. Let's deep dive into the Bracket SDK. So it's an open source Python library that you can use to access quantum computers and build those quantum programs. And we'll actually go and talk about how you can actually build a quantum program and then run it on the QuEra device. You can install the SDK locally, but then we also have local simulators. Not only do we have state vector and density matrix simulators, but we have specific AHS simulators available through Python and then Julia as well. Feel free to scan the QR code to actually learn how you can access these. And then we have the device itself. One thing that we're all about at Amazon Bracket is democratizing access to quantum computers and being able to not only have access to local simulators, but actually build your program and then run it on an actual device allows you to get that holistic end-to-end workflow. And so what is exactly an analog program? What are the features that are available on the QuEra device? And so one thing that we want to point out is the way that this device is built, it allows you to actually play with the atoms on the atomic level. And so those Rydberg atoms, you're able to customize them. You're able to create these custom arrangements. This is just a funny world map here, but you can actually customize these and create different lattices. And what we'll see with one of the customer engagements that we did is, this becomes really useful when you're trying to simulate chemistry. These natural compounds where you can actually manipulate the atoms and design certain lattices. The next biggest feature is these distant dependent interactions. So being able to see, hey, what are the van der Waal interactions between each of these atom states? In addition to these core features that we have available through the device, we have experimental capabilities. Something that Alexei previously mentioned is gaining access to different elements like local detuning, being able to change the shape of the geometries, the distance between the atoms. And one thing that we really want to enable on Amazon Braket is as soon as there's a new feature that's available on a device, we want to get it into the hands of customers. And so, to their name, experimental capabilities are available on certain devices. And here we're just pointing out 3 of the ones that are available on the QuEra device. So why is the analog Hamiltonian device unique? What's so special about it? And as scientists, for scientists, being able to look at the core Hamiltonian, being able to manipulate the atoms and represent different problems is what this device really allows you to do. And pay attention to some of these color codings. So here, we have our Hamiltonian. You can modify the detuning field, you can adjust the amplitudes and the phases, and then you can also specify the locations of the atoms. How does this look in terms of a quantum program? So you have your analog program, and we'll actually go through one really quick. You have your atom arrangement. So your standard XY coordinates, where you can specify, hey, this is how many atoms I want to use, and this is the location of each atom. The next is the Hamiltonian. If you think back to the previous slide, in that formula, there were different, let me go back just so people can see. There were different color codings, right? So you have your detuning field, your amplitude, and your phase. How do these actually map? You can input these as time series. So it's not like a unique point, it's multiple points that you can manipulate over time. And then, let's say you want to go even deeper. You can add on that experimental capability to say, hey, here's a time series, this is the magnitude that I want for a given workload. So how do you actually run a program? It's great to talk about this stuff in theory, but how do you actually use it? And so that's one of the cool things. We're going to be walking through this quick example and then talking about how customers are using it. And at the end, there'll be a QR code that you can actually go read about how this program works and run it yourself on Amazon Braket locally if you'd like. So our setup, imagine each one of these circles is an atom. You have your upstate and your downstate. And so what we're going to be doing is we're going to be preparing the ground state, and then we're going to measure each one of these values. So your AHS program can have 3 components. The first is defining that atomic arrangement that I was mentioning. Again, you can import your coordinates as a list. So it's not like you have to enter one at a time. All of these things that are highlighted, you'll notice they're lists. The next is the Hamiltonian. So actually defining, hey, what are the times, the amplitudes, the phases that I want. All of these come together to say, hey, here's the program. I'm going to call an AHS service. And here's the register that I've defined up here. And here's the Hamiltonian that I've defined up here. And you can run these all in a familiar language, Python for those familiar with the syntax. So you don't have to go ahead and learn a new language or any of that stuff. It's all available in Python. When it comes time to running, again, you can scan the QR code to see how it would actually work. But you have 2 options. Going back to that build, test, run theme that I was talking about, if you're running something small and you only need 12 to 15 qubits, start on the local simulator. So you can see in this Python code saying, hey, this is the number of shots. I want to run it on this AHS device, or the simulator, excuse me, and I can see how that runs. But when I'm ready to scale it up, I can actually go and run it on that QPU. Up to 256 qubits that I want to access. You do have some things that you have to modify when you're running on the actual QPU, but again, you can take that same program that you just simulated and see how it compares. The cool thing about it is the results that you get will show you, hey, what is the location or what's the result that I'm getting for each atom. So it'll either be an empty site, upstate, or downstate. And so when you process your results, when you run them on a device, you'll actually get an output that shows you, hey, these are the counts for each of the states. We've done some post-processing in this example to show out or filter out some of the empty sites, but you're able to see what those counts are. The next thing that I briefly want to touch upon is applications. And so the interesting thing to note about these applications is it's an example of industry working with AWS, working with QuEra to actually solve a concrete use case. And so here we bring in AWS, QuEra, and JP Morgan Chase. They've developed a proprietary hybrid quantum classical algorithm that's focused on the maximum independent set problem. So this is really useful in portfolio optimization. Imagine you're trying to build a portfolio where you have a series of stocks, and those stocks are independent. You can go into like an index fund where, you have some related stocks, but you might want to find the ones that are most optimal and not as dependent on each other. And so what's actually happening here is pretty cool. So you have your input, and you specify your parameters. You have your MIS problem, so that's your standard parameters. You're saying, hey, the first thing I'm going to do is I'm going to run this on a classical computer to try to simplify the problem. I'm going to send it over to the quantum computer. I'll touch upon that in a second of what's going on. And then you're going to have this hybrid quantum classical processing that's working together in parallel. What's happening on the actual quantum computer? So you start by saying, hey, this is how many qubits I want to use. In this case, they had experiments up to 231 qubits. You schedule it, program it as an AHS program, submit it to the QPU, and then you do some quick post-processing on it. And so the real value add that comes out of these kind of collaborations is you can take an existing use case that is common in industry, and you can see, hey, how does this actually map? The next one that I briefly want to touch upon is with Purdue University. So working with Purdue, QuEra, AWS, and Oak Ridge National Lab took a lattice. What I was saying earlier about being able to manipulate the atoms and actually use it for materials discovery or simulation, the cool thing here is, imagine you go and program your AHS device and you manipulate the atoms in such a way that they look like this model, the Shastri-Sutherland model. And what you can do is, you can actually say, hey, rather than getting this physical chemical, going and procuring it, you can actually simulate it and then actually run it on an actual quantum computer to see what those results are. And so think about it. If you're working in the pharmaceutical industry, if you're working in the drug discovery space, and you want to start experimenting and see where quantum computing might be useful, this is a good approach that you can take. And then I'll pass it back off to you to talk about some of the key takeaways. I know we've gone over.
So we just wanted to highlight 3 things that we learned that was kind of the key to success of this whole service. Number 1 is that the features were really driven by customers and use cases. Number 2 is that we continue to operate the machine consistently while developing the operational model itself and the features. And number 3 is that between QuEra and AWS, we really covered the entire value chain from atoms all the way to customers and applications. And today, we believe that's extremely important to really think through that whole stack in order to deliver quantum computing to our users. So with that, thank you so much.